Hello and welcome to Bedroom Physics. This is the example video for fluids, and today I'm going to be doing 3 different problems. One which involves a continuity equation and Bernoulli's equation, one which involves balancing, and one which is just a good bit of fun. Alright, let's jump right in. So in this problem, we have a bucket that has a radius of 7 times 10 to the negative second meters, or 7 centimeters. It has a hole at the bottom with an area of 1.6 times 10 to the negative 4 meters squared, and there's a tube which has water flowing into the bucket at a rate of 2.2 times 10 to the negative 4 meters cubed over seconds. And what we're looking for is the height that the water will fill the bucket to. Of course, it's not going to overflow or fill to the top because there is a hole in the bottom, but overall this is a pretty easy problem. So if we think about it, we're going to be using Bernoulli's to solve for the change in y, but of course we don't have the velocity of the water down here, so we'll have to solve for it, but we can solve for velocity 1 just by dividing the flow rate of the water by the area of the bucket itself. So that's going to be V1 is equal to 2.2 times 10 to the negative 4 meters cubed over seconds divided by radius, and this is a cylindrical bucket, so the area is going to be r squared pi, 7 times 10 to the negative 2 meters squared pi, and that's going to be equal to 1.43 times 10 to the negative 2 meters per second. And in order to solve for velocity 2, we're going to use the continuity equation, which states that area 1 times velocity 1 equals area 2 times velocity 2. So to solve for velocity 2, we're going to divide area 1, velocity 1 by area 2, and that's going to be equal to 7 times 10 to the negative 2 meters squared pi times 1.43 times 10 to the negative 2 meters per second over 1.6 times 10 to the negative 4 meters squared, and that's going to be equal to 1.38 meters per second. And now that we have that, we can solve for y in Bernoulli's equation. And of course, we start off and the bucket is open to the atmosphere, and in the end the water is flowing towards the atmosphere as well. So it's going to be 0 is equal to 1/2 rho v2 squared minus v1 squared plus rho g change in y, and we're trying to solve for change in y, so it'll be negative 1/2 rho v2 squared minus v1 squared divided by rho g. Rho cancels out, and we have negative v2 squared minus v1 squared over 2g, which is going to be equal to negative 9.72 times 10 to the negative 2 meters. And of course, the only reason is that it's negative is because in Bernoulli's equation, when we measure change in y and we're going from top to bottom, it's going to be negative, but really the final answer is just 9.72 centimeters. On to the next problem. Okay, so this problem is a little trickier. We have kind of like a U-shaped tube. On one end we have water, and on the other we have oil. There's a barrier in between them, and the height is 20 times 10 to the negative 2 meters. The specific gravity of the oil is 0.6, so we know that the water is much more dense than the oil, and we want to know what the new heights would be if we remove the barrier. So we have to think about this one as a pressure final. We don't want to go from initial to final. And also we're going to separate the pressures on the left and on the right. And so in the final stage, the pressure on the right is going to be equal to the pressure from the atmosphere plus the new pressure from the new level of water. And since we know water is more dense, we know it's going to lose height. So we're going to go ahead and do rho water g height minus y. And actually this is supposed to be on the left. And on the right side, we're going to have P atmosphere plus rho oil g times the height plus rho water g times the height. And by the height, I mean the new height. So since we're losing height on one end, it's going to go to the other end. And since they're in equilibrium, all we have to do is set them equal to each other. So we're going to have P atmosphere plus rho oil GH plus rho water GY is equal to P at plus rho WG H minus Y. P atmospheres go away and we want to solve for Y. Rho oil G H is equal to rho water GH minus rho water GY minus rho water GY. And then we're going to go to rho oil GH minus rho water GH. And we're going to divide it by 2 rho water G. G's are going to be cancel out. And we're going to be left with rho oil H minus rho water H over 2 rho water. And of course, rho oil over rho water is going to be 0.6. Rho water over rho water is 1. And all we're left with is going to be 0.6 H over 2 minus H over 2, which is going to be equal to 0.3 H minus H over 2. Oop, and it looks like that's going to come out negative. I probably made a mistake somewhere. Yep, this is supposed to be negative right here, and here, 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 here. And of course, H over 2 minus 0.3 H is going to be equal to 0.04 meters. And so the new height of the water is going to be 20 centimeters minus 4 centimeters, and it's going to be 16 centimeters. And the new height of the oil is going to be 20 centimeters plus 4 centimeters, which is going to be 24 centimeters. Alright, on to the next problem. Okay, so lastly we have some sort of reservoir of water, and it is on the floor with a height h, and we want to know at what vertical altitude to drill a hole in it to get the liquid to flow a greatest distance away from the reservoir. So this is actually a pretty neat problem. It's going to involve kinematics. So we know that the change in horizontal distance is equal to velocity times time. And we also know that the amount of time that it's going to take for the water to reach the ground is the amount of time must be solved using kinematics in the y dimension. So we have y final equals y initial, and there's no velocity initial, so we're just going to do plus 1/2 gt squared. And of course, y final is equal to 0, and we want to solve for t. So we're going to do negative y initial times 2 over g squared equals t. And then for velocity, we can solve using Bernoulli's equation. And since the reservoir is open to the atmosphere and the hole is open to the atmosphere, it's going to be equal to 0. And it's going to be equal to 1/2 rho v final squared minus v initial squared. But since the ratio of the area of the reservoir is so much larger than the area of the drilled hole, v initial is going to be 0, and that's going to be plus rho g, and then this is going to be h minus y initial. And actually, since we do measure from top to bottom, this is going to be negative, so I'm just going to put a minus sign right now. And now I'm going to solve for v initial, and it's going to be equal to rho g h minus y initial times 2 over rho squared. Rho goes away, and we're left with 2g h minus y1 over nothing. It's just the square root equals v1, and now we're going to multiply v1 and t, and since these are both under the square root, we could just multiply them like that, and so the g's are going to cancel out, and what we're going to be left with is equal to 4y1, and since this g here, I added it, so it actually is going to be negative, but of course the g from Bernoulli's is always positive, so this negative sign is going to go away, and this g is going to become positive. This whole equation is going to be positive, and h minus y initial square root. Okay, so now we have to find the max distance, and the way that we do that is doing a derivative. So we do dx over dy, and that's going to be equal to 2 4y1 h minus y1 times the derivative, and that's going to be 4h minus 8y1, which is going to be equal to 2h minus 4y1 over the square root of 4y1 minus y1. And of course, if we want to find the max, we're going to set it equal to 0. And of course, the denominator is going to go away, and we're going to be left with 0 is equal to 2h minus 4y1, which means that negative 2h is equal to negative 4y1, which means that y1 is going to be equal to h over 2. So at h over 2, the x is going to be at a max, and when we plug in h over 2 for y1, we're going to get, so that's 2h 0.5 h squared is going to be equal to h. So the y, it's going to be half of the vertical height, and the maximum x distance is going to be h. In any case, this has been the example video for fluids. Hope to see you in the next concept video.